We are from Yashiro High School in Nagano. Now, we are going to present about Matsurosta and the chemistry of calcium carbonate that's contained in granite. This is called Genno Ishi in Japanese. Our presentation is divided into 4 areas. We will present 1. Information about granite and Matsurosta. 2. Details about the crystal found in Matsurosta. 3. The environment of calcium carbonate formation. And 4. Our study trial of making calcium carbonate crystals. These are previous graduates from Yashiro High School. These graduates researched the stone called granite. They discovered that it contained calcium carbonate. They also discovered that granite is a calcite boric crystal. So we were interested in this stone and we tried to find out how this stone has been made in the shell. We found there are also blocks of calcium carbonate at Matsurosta near our school. This is a picture of the block. The block is stuck into the inside of the pipes that the hot water passes through. We visited Matsurosta and looked into the situation there. The specific features of the water from Matsurosta are that it contains a lot of HCO3- ions and no CO3- ions, which is unusual in comparison to the water from other hot springs. This is our idea how the blocks has grown in the pipes of Matsurosta. Please look at this figure. There are CO2, H2O, and ions in the ground under high pressure. The pressure is released as they gush out of the ground. The water flows, the CO2 escapes, and the HCO3- ions and Ca2+ ions join to create calcium carbonate. We paid attention to this point, and we did an experiment to dry and reproduce similar blocks of calcium carbonate. This is the system that we thought of.
In this experiment, we made conditions nearly the same as those of Matsushiro. For 2 weeks under this system, we measured pH in the water tank, the weight of solute in the water and the temperature. This figure is a result. The weight of solute in the water increases slowly, so these limestone in the tank were dissolved. But we were not able to reproduce the block of CaCO3. 6 days after, we stopped the injection of CO2. A lot of CaCO3 appeared on the water surface in the water tank. Next, we considered what kind of deposit of calcium carbonate occurs at defined pH level. We mixed these 2 solutions. One is CaCO2 with HCl. The other is Na2CO3 with NaOH. In these 2 experiments, we observed that the calcium carbonate deposit appeared at pH 8 solution. We performed more experiments to find out what pH level is good to grow crystals. We used the same materials and tried to slowly diffuse these materials through aggregate. After leaving them for a month, white deposit appeared at pH 7, 8, and 9. In particular, we recognize the Liedekan phenomenon that contain many small crystals in layer at pH 8 and 9 solutions. We thought that to form big calcium carbonate crystals, pH 8 and 9 level would be too high, because the concentration of CO3 ion is high, so calcium carbonate deposit appears quickly. Therefore, we concluded that pH 7 level is the best to form big crystals.
We tried to form big crystals of calcium carbonate by using some kind of gels without thinking about pH levels. The purpose of using gel is to slowly diffuse the Ca2 plus ions and CO3 minus ions through these gels. We use gels such as silica, gelatin, and agar. We also tried to use the mud that was from the shell surrounding the granite. But the mud was so watery that we couldn't use it as a gel, like the other gels. We set up this experiment and left it for a long time. After 2 months, we found the gelatin gel bottoms was covered with mold, and we were disappointed. However, we considered that maybe many crystals existed in the gels, so we continued our experiment. We took out each of the gels and dissolved them with hot water several times, and finally we got a lot of white powders. The reason we used hot water is because calcium carbonate is insoluble in water. To our delight, we were able to observe the white powders by using a microscope and found many small crystals in each powder. Our microscope is not very good, so we went to Shinshu University and took pictures of these crystals through an optical microscope, and we obtained pictures using a scanning electron microscope, SEM, and analyzed them by means of XRD. Please look at these pictures of the result. As you can see, silica is the best to form crystals. We also found that different shapes of crystals were found in different gels. For us, this is a very interesting discovery. In silica, beautiful square-shaped crystals and sphere solids appeared. In gelatin, crystals were not so beautiful. They had a less square-shaped and rough surface. In agar, crystals like oval ball appeared. So we thought that the type of gels has something to do with the formation of crystals. The formation of crystals depended on the type of gels. These are magnified SEM pictures of spherical solid in silica. We thought that this spherical solid may be baterite. Baterite is not stable. う一度このスライドの説明をさせていただきます。There are magnified SEM pictures of spherical solid in silica. We thought that this spherical solid may be batterite. Batterite is not stable in aqueous solution under Earth's surface conditions and transform within a short period of time. We tried to find out what substance the crystals are composed of through elemental analysis. This figure is the XRD chart. This chart shows that each crystal in silica, gelatin, and agar are all calcites. But only in silica, we recognize that there were quite little amount of batterites.
To conclude our presentation, we will summarize our findings. In water, calcium carbonate crystals are able to be formed in several kinds of gels to slowly diffuse Ca2 plus ions and CO3 2 minus ions through these gels. The formation of crystals depends on the type of gels. Silica is also especially suitable for forming a single crystal of calcite. We tried to form big crystals, but we couldn't. To form big crystals, it is essential to use gel carefully, and it may be suitable to set about pH 7. On the other hand, in Matsuroska, calcium carbonate crystals appeared at pH 6.5. We think Matsuroska is an example of calcium carbonate appearance from acetic saline. This chemical equilibrium goes to the right and crystals appear. We want to know how the granite grows, and we try to form big crystals like granite by using shell in the future. That's all. Thank you very much for your attention.
ありがとうございました。それでは質疑応答へと移らせていただきます。ご質問のある方は挙手をお願いいたします。はい、ではマイクをお持ちいたします。
日本語でいきます。今回、流速とかですね、そういうことは条件なしに、普通に、実験を行ったということですけれども、今回pH が8の時にですね、白濁したということですけれども、それ以外にですね、何か沈殿物がなかったのかというのが1点とですね、もう一つは実際に、流速のある条件下で、本来は結晶しますよね、そういうパイプの中で。それと実際に今回の実験例の対象としてですね、本当にそれが、実用化できるのか、どこにて教えていただけますか。
ご質問ありがとうございます。1つ目の質問は、pH8 の時に他の沈殿ができたかということなんですけど、この実験の後に水を蒸発させて残った結晶を観察したところ、四角い結晶ができました。それは一応 NaCl ではないかと考えているんですが、正確には調べてないので分かりません。
今回、流速、こちらの実験でよろしいですか。松代温泉の条件下だととても大規模になってしまって、私たちはその大規模なところを再現できなかったので、流速としてはとても遅いです。あと、その水温なんですけど、松代温泉と比べて、低かったので、炭酸カルシウムの析出ができなかったのではと考えています。 なのでこれからこの実験を真白温泉と似せていくためにはこの流速とかを考えなければいけないんですけど、ちょっと化学室内での実験には難しいかなと考えています。
わかりました。ありがとうございます。
ありがとうございます。その他ご質問ございますでしょうか。はい、ではマイクをお渡しください。
Thank you very much for your interest. My name is from Op6 University. Could you show me the slide number 4? I have interest in the hypothesis in could you tell me what is the role of ferric I1 Fe2? How it works for the crystallization?
ご質問ありがとうございます。CN2 プラスのイオンっていうのは、地上に出て温泉として出てくるときに CA3 プラスになって出てくるんですけど、その時にこの温泉の色が茶褐色なのが分かっていただけると思うんですけど、この色がその Fe2 プラスのイオンが出てきて変わって CA3 プラスのイオン、すみません、Fe3 プラスのイオンによりこの色になっています。
Thank you.
ありがとうございます。その他ご質問の方はよろしいでしょうか。ではお時間参りましたので以上とさせていただきます。長野県八代高等学校の皆さんでした。ありがとうございました。